A rather simple elementary class of equations is first order linear equations with constant coefficients. So we're thinking of differential equations of this form: y prime plus p of x y equals q of x. These, it turns out, can be exactly solved by a couple of different methods. The first method I'll describe is known as the exact function method. So for those who have taken differential equations, this might just be a review. So I'll write this first as y prime as dy by dx. So this is going to look like dy plus negative q plus py dx equal to 0. And I'm going to suppress the dependence of p and q on x just for the ease of writing. Now, if this system is exact, then you can write this as the differential of a single function. However, that is not the case here. So if I had a function u of x comma y that's exact, that means du is 0. That's what the exact function means. Then I can write this as ux dx, where subscripts refer to partial derivatives, plus uy dy. And then I can identify ux with whatever you have there and uy with whatever you have here. But exactness requires that ux and uy satisfy what's known as the condition of exactness. And that condition is that uxy equals uyx. In other words, the mixed partial derivatives commute, and this is sometimes referred to as Clairaut's theorem. So Clairaut's theorem is a necessary and sufficient condition of exactness. However, unfortunately in this case, Clairaut's theorem is simply not satisfied. So we have to multiply it with some factor known as the integrating factor. The integrating factor is of different types in different problems, but the most simple integrating factor, we can take it to simply be a function of x in this case. This works out. Integrating factor is an art. You don't really know this up front, but you try various things out and one of them works. So let's try multiplying both sides of this differential equation with a function known as mu. So mu times dy plus mu times negative q plus py dx equal to 0. I want to enforce exactness. So what I'm going to do is, let me try writing what del mu by del x is. Okay, so this is uy dy. So uy is equal to mu. So I need uyx, and that's going to be del mu by del x. And since mu is just a function of x, that's simply going to be d mu by dx. The partial derivative becomes the ordinary derivative. And that's equal to uxy. Ux is whatever multiplies dx. So the partial derivative with respect to y of this, well, mu is just a function of x, so the partial derivative with respect to y does not act on that. Q is also a function just of x. P is also a function just of x, so it only acts on the y term. So I'm going to get, this is equal to mu times p. So now I have a really interesting equation, d mu by dx equal to mu times p. So that gives me d mu by mu equals p dx. I can integrate both sides, and I end up getting natural log of mu equals p dx, the integral of p dx. Now, you might think, what about the constant of integration? But I would say, don't worry about the constant of integration, since the right hand side is 0. So we can write this factor, integrating factor, as mu of x equals e to the integral p dx. Amazing. So now let's write down what the du is. Du is del u by del x dx plus del u by del y dy, and that's, if it's equal to 0, then it's exact differential. So let us try to identify the du by dx and du by dy. So I have two possibilities. I can write this as del u by del x equals whatever multiplies dx, so that's going to be mu times negative q plus py. That scares me. The other equation is del u by del y is whatever multiplies dy or mu. Well, that's easier to deal with. You'll all agree with that. So I'm going to write this as I'll immediately integrate this. So it gives me u equals some, first of all, it's going to be mu times y plus some constant. That constant cannot just be a constant, it needs to be some function of x. So now I'll differentiate with respect to x and set it equal to this. So that's the usual trick in partial derivatives. So del u by del x is now going to be, well, y is a function of x, as is mu, so we've got to be careful here. That's the partial derivative with respect to x though. The partial derivative with respect to x will only see things that are explicitly dependent on x, not implicitly. So y will not be affected. So that's going to give me y times mu prime plus h prime, because h does explicitly depend on x. And this has to be compared against that. So I'm going to get that is equal to negative mu q plus mu times py. So the upshot is that you're going to compare these two things, and mu prime, when I differentiate with respect to mu, I'm going to get p times mu. So mu prime is just p times mu. So I'm going to get this and this to be equal, which means that h prime equals minus mu q. And that tells us that h equals the integral, negative integral of mu q dx, where I'll take the negative sign inside, minus q. Mu itself is e to the integral p dx. So you're going to get this really awful looking thing. So the full solution, u of xy, is going to be y of x times e to the power integral p dx minus the integral of q. We're going to look at that, q times e to the integral p dx. And that u equals constant, because if du equals 0, then u equals constant. So that's the full solution of this differential equation. So that's a pretty elaborate looking solution. All you now have to do is solve for y. So y can be solved for by taking this to the right side. So y gives me y times e to the integral p dx equals all that stuff. So let me just write one more step. Y times integral p dx equals c plus integral q e to the integral p dx, which tells me that y equals e to the negative integral p dx times c plus integral q times e to the integral positive integral p dx. So this is the full solution of this differential equation. In practice, you never do this. You solve it as though you're seeing it for the first time, find the integrating factors, and proceed like that. Now, there's a second way of doing this, and it is by the Lagrange method of variation of parameters. So let's try it like that. So this is the second method. Both methods are equally valid, and there's no need to prefer one method to the other method, but it's really nice to see the interaction between these two methods. They contain the germ of one is contained in the other. So y plus p of y equals q is the differential equation. Once again, I'm suppressing that p is a function of x and q is a function of x. Now what Lagrange's method entails is solving the homogeneous equation first. So y prime plus py equals 0 is a homogeneous equation. Well, that's immediate. So I get y prime over y equals negative p, or dy by y equals negative p dx, or y equals the natural log of y equals negative integral p dx. Now we do need a constant of integration, otherwise this method won't fly. So when I solve for y, I'm going to write this as y homogeneous equals constant times e to the integral negative integral p dx. You see the kinship between these two methods. You have the integrating factor in that case, which is the integral of p dx, whereas here you have integral of e to the negative integral of p dx times some constant c. There we never bothered to put the constant c because we knew that we were going to have all these other constants coming in anyway at the end due to the exactness of this potential function. Here you do have to explicitly put the constant c in. So these are the various fine points you have to note when comparing the two methods. Now the full solution by Lagrange's ansatz is the constant c as written as a function of x. That'll be the full, c as a function of x. That'll be the full solution. Let's actually find out what y prime would be. Y prime would be c prime e to the minus integral p dx, and now I leave c alone, and then I differentiate that. Well, that gives me a negative p times e to the negative integral p dx back, because that's what exponentials do. And that's y prime alone. So y prime plus py equals q. Let's solve that. C prime e to the minus integral p dx minus pc e to the minus integral p dx plus, look at this, plus pc, because y homogeneous is, y of x is again c e to the minus integral p dx. So these two terms are going to cancel. Equals q. Well, that's very nice. So I just get c prime equals q times, when I take this to the other side, it becomes e to the positive integral p dx. Look at that. It's right there. And now c itself is going to be some other constant, c naught, I'll call it, plus the integral of q e to the integral p dx. It's a miracle. It's the same thing. And the final solution of this differential equation is c of x stuck in there. So y of x equals c of x, which is c naught plus integral q e to the integral p dx times e to the minus integral p dx, which is exactly the same as that, except I put the bracketed term before I put the other term. So they agree. The Lagrange's method of variation of constant agrees with the method of potential theory, which is to find a exact differential employing Clairaut's theorem.